This is the Water Quality Association podcast.
What's nice is that iron lets us watch this hidden chemistry happen, but with other contaminants, the same kind of change may be invisible, but sometimes the consequences are even more serious than we expect.
That's Dr. Joshua Mertz with LaMotte Company talking about using smarter water analysis to unmask contaminants. And welcome to the podcast from the Water Quality Association, the leading voice of the residential, commercial, and industrial water treatment community. Find us at wqa.org. I'm Wes Bleed. Be sure to like and subscribe to the podcast so you never miss a show, and be sure to share it with someone on your team. And a reminder, you can watch our podcasts on YouTube. In this podcast, we feature portions of a recent WQA webinar entitled Hidden Chemistry, Unmasking Contaminants with Smarter Water Analysis. The webinar explored how different forms of manganese, iron, lead, and arsenic can influence test results, complicate treatment decisions, and affect system performance. The presenter was Dr. Joshua Mertz of LaMotte Company, a global leader in water analysis solutions. Plus, we'll have our WQA tip. It's all coming up on the Water Quality Association podcast. Water test results may identify iron, lead, arsenic, or manganese, but the name of the contaminant doesn't always tell us how it will behave or how it should be treated. In a recent WQA webinar, Dr. Joshua Mertz, Director of Research and Development at LaMotte Company, explained what he calls the hidden chemistry of water. We've selected a few excerpts from the webinar that illustrate why the form of a contaminant can be every bit as important as the element itself.
So many of us have collected clear well water and watched it turn orange over time. Specifically, we look at that water, we say, okay, this water is not turbid, it's wonderful. And then over time, we see it change color. And as a budding chemist, you might think, well, why is that happening? What do we see? Why is it changing? And I'll tell you that this talk is really central to this idea is really central to this talk, that the periodic table will name the element, in this case, iron, but water chemistry will determine the form we measure and the treatment that will work. So from this instance, we have iron that's iron 2+, it's completely dissolved. And as oxygen gets into the mason jar, we see the precipitation from oxidation from iron 2+ to iron 3+. And finally, we can get iron hydroxide type solids. We'll go into this in a little bit more detail. What's nice is that iron lets us watch this hidden chemistry happen, but with other contaminants, the same kind of change may be invisible, but sometimes the consequences are even more serious than we expect.
That distinction becomes much more consequential when the contaminant is lead. A test result can tell us that lead is present, but Mertz says that is only the beginning of the treatment question.
So today's talk is going to focus mainly on lead. I also talk about iron and manganese, and I really want this to hit home. The name of the element is only a part of the story, right? If we have lead in water, it's not just lead in water, it's different types and compounds of lead in water, and that really makes a difference. Different environments invoke different chemistries and significantly different treatment decisions. Now, moving to lead, the consequences, again, chemistry wrong can be really tragic. So let's first talk about lead in any form. So lead in any form is toxic. There are different mobilities of lead. We'll get into that in a little bit. But just from a health effects standpoint, the World Health Organization looks at the toxic effects of lead, focusing mainly on the blood, kidneys, reproductive organs, and brain damage. And if you're a parent out there like I am, I'm really concerned of lead being exposed to my children. And that's because there are a lot of neurotoxic traits that come with lead. So we try to make sure that our lead is not in our drinking water. There are lots of ways to treat lead, but we have to understand the chemistry first. So when people are concerned about lead, especially after Flint, Michigan, we get our water tested. In Delaware, the state gets our children tested for lead in our blood. We also get our municipalities send out a lead report, and actually our school systems also send out a lead report. And when there's a flag, there's a lot of concern. So we get a test report that says there's lead in my water. Usually the first question a customer of mine might ask is, how do we treat the lead? But as a chemist, I stop thinking about how to treat the lead and I start thinking about understanding what form of lead exists first, because that dictates how I'm going to treat it. So we also don't want to just define how much lead is in there, but we also need to understand what kind of lead, right? And just as a reminder, no form of lead is healthy. That's why the EPA regulates it so tightly. We want to make sure that lead is not getting to our biological systems.
The Flint water crisis offers a familiar example of what can happen when changes in water chemistry disturb a system that had previously kept lead from entering the water.
Just like we learned that Porbet diagrams can help us stabilize the cationic form of lead, it can also help us prevent corrosion. And the best way to talk about this really is the Flint, Michigan case study. So Porbet diagrams can tell us how to stabilize lead. And if you look at what happened before the city changed the water from Detroit water to Flint River water, the municipality was using a phosphate inhibitor. It was added to the water. Basically, it created a scaled surface of lead phosphate on the surface of a lead pipe. That was awesome. Lead was not mobilized. Even if they had chlorine in the water, it basically stabilized that lead so that didn't get to the households. Now, when they switched to Flint River water, the chemistry changed, and the Porbet diagram basically said, okay, our water no longer has phosphate in it, and we have all these chlorides. Well, the chlorides and the oxides reacted with that scale and essentially released the lead. That can release in a couple different forms. This infographic shows that it's releasing as a divalent lead. And so those high chloride levels and lack of phosphate created lead speciation release. Corrosion and redox chemistry are really important to water treatment, water analysis. And so we can also take this back to corrosion in iron and iron pipes. It can happen the same way. So let's go back to our hidden chemistry. Our hidden chemistry of iron basically says that when we take a sample from a well, we need to understand the ORP and the pH. And that over time, that ORP is going to change and the water is going to become oxidized because it's being in contact with air. So we have iron 2+ in A, then slowly it transforms into iron 3+, and then it slowly transforms into iron hydroxide. Now, when I talk to other people, I often mislabel the iron as rust. It's not technically rust in this case, but be aware that there are many forms of iron hydroxides. And so we'll go to the Porbet diagram to understand that even though the element stayed the same, the chemistry that we are looking at has changed dramatically.
These excerpts introduce the central point. Accurate water analysis requires more than identifying an element. Its chemical form, the surrounding water conditions, and even the way the sample is collected can affect both the reported result and the appropriate treatment. You can view the complete webinar, including Dr. Mertz's discussion of sampling methods and treatment considerations, on the WQA website. Visit wqa.org/webinars, then click on the View Past Webinars button at the bottom to be taken to a list. You'll be prompted to sign in. If you're not a member, consider joining WQA. You can also click on the View Upcoming Webinars button to see what's next. Our WQA tip. WQA members have access to the Member Learning Library, a new membership benefit offering exclusive training videos at no additional cost. The library features short, focused courses designed for busy water treatment professionals with topics that can help build knowledge and support real-world problem solving. Eligible courses also offer up to 0.25 CPD credit for WQA certified professionals. Go to wqa.org/membership and look for the link to the Member Learning Library. Thanks for joining us for the Water Quality Association podcast. Learn more about water and water filtration at our consumer website, betterwatertoday.org, and learn more about professional certification, the Gold Seal Product Certification Program, and how you can become a member at wqa.org.